So in today's lesson, we will be looking at diastereoisomers. Diastereoisomers are stereoisomers that are not mirror image of each other. They have the same molecular formula and sequence of bonded atoms, but differ in their 3D arrangements of atoms in space. They are like molecules that have multiple chiral centers. Those are carbon atoms attached with 4 different groups, and they differ in their configuration at one or more of these centers, but not all. Looking at diastereomers. Diastereomers are 2 molecules which are stereoisomers of each other, same molecular formula, same connectivity, but different arrangement of atoms in space. They are like enantiomers, which are mirror images of each other and non-superimposable. Diastereomers are not mirror images of each other and are non-superimposable. Diastereomers can have different physical properties and reactivity. They have different melting points and boiling points and different densities. Examples are trans-2-butene and cis-2-butene. These are diastereomers because they have the same atoms connected in the same sequence, but a different spatial arrangement around their double bond. We also have cis and trans 1,2-dichloroethene. They are diastereomers. They have different chemical and physical properties. Still considering trans 1,2-dichloroethene and cis 1,2-dichloroethene, let's consider their features. Their boiling point, cis 1,2-dichloroethene is approximately 60 degrees, while trans 1,2-dichloroethene is approximately 48 degrees Celsius. Melting point, cis 1,2-dichloroethene melts at about 80 degrees Celsius and trans 1,2-dichloroethene melts about 50 degrees Celsius. Dipole moment, cis 1,2-dichloroethene has a net dipole moment, which makes it polar. Trans 1,2-dichloroethene has no dipole moment, so it is nonpolar. Solubility in water. Cis 1,2-dichloroethene is slightly more soluble due to polarity. Trans 1,2-dichloroethene is less soluble because it is nonpolar. And then stability. Cis 1,2-dichloroethane is less stable than trans due to steric repulsion between chlorine atoms on the same side. The trans 1,2-dichloroethane is more stable due to less steric hindrance with chlorine atoms on opposite sides. Let's look at this example of D-glucose and D-galactose. It's an example of molecules with multiple chiral centers. When a molecule has more than one stereocenter, for example, D-glucose and D-galactose, it can have diastereomers. If the stereocenters have different configuration at some positions, but not all. D-galactose and D-glucose have 6 carbons each with 4 chiral centers at carbon 2, carbon 3, carbon 4, and carbon 5. So they can form what we call epimers. Epimers are diastereomers that differ in configuration at only one of the multiple stereogenic centers, usually an asymmetric carbon atom. D-glucose and D-galactose are diastereomers or epimers because they differ in the configuration of just one of their chiral centers. For D-glucose in carbon 4, it has a difference of the OH group is on the right, while in D-galactose, the OH group is on the left. So these are examples of multiple chiral center molecules, D-glucose and D-galactose. Let us look at the Meso compound. A meso compound is a type of stereoisomer that has chiral centers but is optically inactive due to an internal plane of symmetry. An example is 2,3-dichlorobutane. It has an internal plane of symmetry as shown on this slide. Another example is tartaric acid. Tartaric acid has two chiral centers. One of it forms a meso-tartaric acid. The mesoform has an internal plane of symmetry right in the middle. So the two halves of the molecule mirror each other and cancel out any optical activity. This makes it optically inactive even though it has chiral centers. So the mesoforms of compounds are always optically inactive. NMR of diastereomers. Different chemical shift. The isotropic protons, which are protons in different chemical environments, will have different chemical shift, leading to distinct signal in the NMR spectrum. Distinct coupling constant. The coupling constants, that is the J values, between protons will also be different for diastereomers, further distinguishing them apart. Multiple signals. A mixture of diastereomers will show a complete set of signals for each individual diastereomer, which is in contrast to enantiomers, which are indistinguishable by NMR spectroscopy, except using chiral agent. What are the differences between enantiomers and diastereomers? Their relationship. Enantiomers are non-superimposable mirror images. Diastereoisomers are stereoisomers that are not mirror images. Physical property. Enantiomers have the same melting point, boiling point, solubility, etc. But diastereomers have different melting point, boiling point, and solubility. In case of optical activity, enantiomers retain plane polarized light in equal but opposite directions, while diastereomers have different optical rotations. Reactivity. Enantiomers are identical in an achiral environment. Diastereomers are different in an achiral environment. Stereocenters. Enantiomers can have one or more stereocenters, but all stereocenters must have the opposite configuration. Diastereomers have two or more stereocenters, which at least one being the same and another being different. Study questions. We have some study questions here. We have say what type of molecules are in ABC. They are there showing on that slide. And then another question says, draw the diastereomer of the structure 1,2,4-trimethylcyclohexane. How many chiral centers are in 2-chlorobutane? Another question there says, draw the structures of D-ribose and D-arabinose. What type of diastereomers are they? Thank you for watching this video to the end. Appreciate if you can subscribe, share, or comment on this video. Expect another lesson soon.